Hey folks, it's your friendly heavy physics teacher here again. This time with a lesson that is going to be another double up lesson because it's dealing with critical angle and total internal reflection. And for the Regents class, this is your Unit 12, Lesson 4. For the college physics class, this is your Unit 11, Lesson 5 material. Okay? So we're talking about critical angle of incidence and total internal reflection today. Now, this is a refractive phenomenon that happens only when you're going from a higher index of refraction medium into a lower index of refraction medium. And what can happen is that instead of the energy of the wave hitting the boundary and some of it reflecting and the rest of it going out into the new medium and getting bent as it goes out into the new medium, if you are above a certain critical angle of incidence, instead of any of it going out into the new medium, none of it does. And you get total internal reflection. In other words, the light ray will come into the boundary and all of it bounces off the boundary and remains in the incident medium. In other words, the boundary is acting like a mirror. Okay? All right, so remember, this can only happen when you go from a high index of refraction medium into a low index of refraction medium. Okay, so critical angle of incidence. It is the angle of incidence at which light will cause a refraction of 90 degrees to happen at the boundary. In other words, if the light's coming in like this to the boundary of the medium, the refracted wave won't go out behind this boundary. It'll go right along the boundary. So at this particular critical angle, if you are less than this critical angle, if your incident angle coming in is less than your critical angle, you get normal refraction, okay? And the refracted angle is going to be larger than your incident angle. But you can get to a point where that refracted angle, as this incident angle gets bigger and bigger and bigger compared to the normal line, the refracted angle gets bigger and bigger to the point where it becomes 90 degrees. So if your incident angle is greater than that critical angle, you can't have an angle greater than 90 degrees, or technically, it becomes a reflection. And so that's what we mean by total internal reflection. The light energy is coming in. If it's less than that uh, uh, critical angle of incidence, it goes out into the next medium normally. If the incident angle is greater than your critical angle, instead of it going out into the new medium, it stays in. It's total. The total energy is reflected off of the boundary. Okay, I need you to get out the critical angle of incidence worksheet that I sent to you. And I need you to take some time now to calculate the angle of refraction for each of these angles of incidence. Use Snell's Law. The medium is we're going from water into air. So the index of refraction of water is 1.33, and the index of refraction of air is 1.00 to 3 significant digits. Okay? So I want you to take some time, use your calculator, use Snell's Law, and calculate these values here. Okay? I'm going to calculate them and fill them in here in a moment. So you thought I would fill them in right away, did you? Fooled ya. Come on, do your work. Get your work done. All right? Here we go. All right, I'm gonna take some time off here. Let's get your work done. What? You didn't fill them in yet? No. Come on, you got to do the work first. Then I'm gonna fill them in. No fair waiting for me to do all your work for you. Come on, get your work done. Didn't get any emails. So I guess you all were able to get these filled in. All right, give me a moment. Let me write them in, and um, we'll compare notes. Okay, here we go. All right. So for 10 degrees, you get an angle of refraction of 13.4 degrees. For 20 degrees, 27.1 degrees. 30 degrees, 41.7 degrees. 40 degrees, 58.7 degrees. And 50 degrees, I got an error. All right. And when you actually, if you just calculate 1.33 times sine of 50, you get a number that's greater than 1. Can you take the inverse sine? Can you take the arc sine of a number greater than 1? You're right. So that's why we've got an error there. Okay, so let's refine this down a little farther. Okay, so go to the next part of the page and use Snell's Law again. And we're going to find out which degree that error happens. Okay, so start at 45 degrees, 46, 47, 48, 49. Obviously, with this, we're looking for either the error to be 47 to 48 or 48 to 49. Okay, so go ahead and make your calculations, and I'll be right back. Did you do your calculations? I've been off doing stuff. Yeah, of course, I get to pause this. Okay, and you can pause it too. So why don't you pause it, do your calculations, and come back? All right, check them with what I got. Just don't let me do all the work. Okay, here you go. All right, hopefully yours checked with mine. Okay, so for 45 degrees, you get a 70.1 degree angle. For 46, 73.1. 47, 76.6. For 48, notice it starts climbing, 81.3. And then between 48 and 49 degrees, the angle goes over 90 degrees. Okay, in other words, somewhere between 48 and 49 degrees, instead of refraction, we get total internal reflection. Okay, so that the reflected angle is going to be equal to whatever this incident angle in between 48 and 49 degrees is. So, how do we calculate what this critical angle is? All right, without having to go through all this rigmarole of, all right, in between what two angles is it going to happen? Okay, so since we know that at the critical angle, the refracted angle has to be 90 degrees, that means using the Snell's Law equation, the incident medium times sine of the incident angle equals the refracting medium times the sine of 90 along the boundary in between the two mediums. Okay? If we do the algebra of this, then that means that the critical angle is equal to the inverse sine of the refracting medium's index of refraction divided by the incident medium's index of refraction. Notice that this only works if N2 is less than N1. You get a weird number over here if it's not. Okay? You get an error. All right? Because if you say N2 can be greater than N1, then you're going to be taking the inverse sine of some number larger than 1. You can't do that, okay? So critical angle only happens when you go from a high index of refraction, N1, into or attempt to go into a low index of refraction, N2. All right. So we've got all of the information that I want to cover right now for refraction. And so I'm going to be sending out a content review on everything on refraction for the college physics guys. It's going to include stuff on the mirrors. All right. And we're going to really hammer this down and get your knowledge base down with this. Okay. So be on the lookout for that. Also be on the lookout for the lab, the refraction labs, the refraction labs. Okay, so one of the applications for this is in fiber optics. All right, if you take a transparent material and make it into a tube, all right, but it's a solid tube of, it's not a hollow pipe, but a solid piece of transparent material, but make it like a rod. Okay, and you shine a light in one end, the light will come out the other end, and none of it escapes the sides, or very little of it escapes the sides. Okay, you can then bend that rod, and the light will follow it, because no matter how you work it, the light will always be making a critical angle with the side of the transparent material and the air. And it will always be greater than that critical angle. So you get total internal reflection down the length of the fiber optic. All right. And so that's how fiber optic cable is used. You can think of it as a light pipe. All right. You shine a bright light at one end, and the transparent material carries that light down the length of the tube with little or none of it escaping through the sides, because the pathway is always going to be greater than the critical angle between the side of the fiber optic material and the air that's surrounding it. Kind of cool, huh? All right. I encourage you to look up fiber optics on the web and see some applications of that. See how people are, pointing the laser in one end, and you see the laser come out the other end. Okay. I have some at school. Unfortunately, I'm not going to be able to show it to you from school. All right. I'm going to see about getting into school and see if I can pick up some of my equipment. And I'm going to do, if I can get a lot of it, I'm going to do some demo videos and see what we can do with that way. All righty. This has been your friendly heavy physics teacher once again. Unfortunately, I will not see you for the remainder of school year 2019-2020. Seniors, hopefully we'll do something for you, and we'll make it special. Have a great one, folks. Bye-bye.